Welcome to Inorganic Chemistry. Today, we are going to explore crystal ion packing. Imagine trying to pack as many tennis balls as possible into a cardboard box. If you just throw them in, you leave a lot of empty space. But if you carefully arrange them in neat, nesting layers, you can fit many more. In nature, atoms and ions act exactly like these tennis balls, packing tightly to maximize their electrical attraction and stability. Now that we have our tennis ball analogy, let us look at how this works chemically. In a solid lattice, anions are usually much larger than cations because they have gained electrons. Therefore, these large anions form the main structural framework by packing tightly together in close-packed structures like hexagonal or cubic arrangements. However, they cannot fill 100% of the space. They leave small empty gaps known as interstitial voids. The smaller cations then slip into these empty voids to complete the crystal structure. This brings us to the specific types of gaps created. When large spherical anions pack together, they create two distinct types of empty spaces where cations can hide. The first is a tetrahedral void, which is a tiny space trapped between just four touching spheres. The second type is an octahedral void. This is formed by a gap between six surrounding spheres, making it noticeably larger. Nature automatically places smaller cations into the tetrahedral voids and larger cations into the octahedral voids to ensure a perfect stable fit. Before we move on to the math, let us see this with a concrete visual. On the left, you can see the tetrahedral void. Notice how small it is, trapped tightly between only four touching spheres. In contrast, look at the octahedral void on the right. It is noticeably larger because it is formed by a gap between six surrounding spheres. If a cation is too large for its void, it will force the packing atoms apart and destabilize the entire crystal. Now that we understand what these voids look like, let us define the mathematical rules for them. We can relate the number of these voids to the total number of packing atoms. For octahedral voids, the formula is NO equals N. Here, NO represents the total number of octahedral voids and N represents the total number of large packing atoms, usually the anions. This tells us a straightforward rule. For every single packing atom in the crystal, exactly one octahedral void is created. If the crystal grows, the voids increase by the exact same amount. This formula we just saw leads us to the rule for the other type of void. For tetrahedral voids, the formula is NT equals 2 times N. NT stands for the total number of tetrahedral voids, while N again represents the number of large packing atoms. This equation shows us that tetrahedral voids are twice as common as octahedral voids. Because they are smaller and more numerous, a crystal has a lot of flexibility in how it places its small cations, leading to a vast variety of chemical formulas. Now that we have our void formulas, let us apply them to a classic problem. In a certain compound, oxide anions form a closed-packed lattice, and metal cations, M, occupy exactly half of the available octahedral voids. What is the simplest formula? We start by letting the total number of oxide anions equal the variable N. Using our established rule, the total number of octahedral voids is also exactly N. The problem states the metal cations only occupy half of these voids, so we multiply the total voids by 1/2. Continuing with our calculation, we substitute N to see that the number of metal cations is exactly half N. Now, we compare the amounts directly by setting up a mathematical ratio of cations to anions, which simplifies to 1/2 to 1. To get whole numbers, we multiply both sides by 2, giving a final ratio of 1 metal cation for every 2 oxide anions. This tells us the crystal perfectly balances its charges and space by using 1 metal atom for every 2 oxygen atoms, giving the final formula MO2. Let us look at a slightly more complex scenario, common in geology, where multiple metals share the same framework. Here, sulfide anions form the lattice. Cations of type A occupy one-third of tetrahedral voids and type B occupy all octahedral voids. We start by setting the sulfide anions to N. Next, we calculate the tetrahedral voids, which are always twice the packing atoms, giving 2N. Since cation A occupies one-third of these, we multiply one-third by 2N, showing there are 2/3 N of cation A. Moving forward with this complex mineral, we now look at cation B. The problem states it occupies all of the available octahedral voids. Since the total number of octahedral voids is equal to n, the number of B cations is simply 1 multiplied by n. Every single octahedral parking space is filled. Now we have the amounts for all three ions in terms of n. So we set up our raw ratio of cation A to cation B to the sulfide anion, which is 2/3 to 1 to 1. To finish finding the simplest chemical formula, we need to remove the fraction from our raw ratio. We do this by multiplying every part of the ratio by the number 3. This gives us a final, clean whole number ratio of 2 to 3 to 3. Therefore, the chemical formula for this complex mineral is A2B3S3. This final answer shows exactly how the different atoms balance out to create a stable, neutral crystal structure. Now that we have successfully calculated these formulas, we must ask why this matters. Understanding crystal ion packing is absolutely crucial because the physical properties of a material depend entirely on how its atoms are arranged. For example, how tightly ions are packed directly determines the density of a metal. Furthermore, the specific packing dictates how a crystal will break or cleave when struck. In modern technology, it even determines how well semiconductor materials conduct electricity, making this the foundation of designing computer chips and solar panels. Let us review the key takeaways from our exploration of crystal ion packing. We learned that nature organizes spherical ions into space-efficient structures, where large anions form the main framework. This creates a predictable number of empty spaces, with tetrahedral voids being exactly twice as numerous as the packing atoms and octahedral voids being equal in number. By calculating how these voids are filled by smaller cations, we can determine the exact chemical formula. Mastering this allows us to understand and engineer the materials of the future.